Okay, so what we're gonna go through now is how is it that we could find the center of a circle if we're given the circle without its center. So we have some circle and we want to determine where the center is. So basically, we don't want to just sit here and guess. We don't want to say that, oh, here's the center. It looks like that's the center, there's the center. No, we want to make it mathematically 100% that we have an accurate representation of the center for any given circle. So here I've drawn a circle. And what we're first going to do is we're going to prove a theorem. We're going to say that if, I don't know, if AB, let's say, is a chord of a circle, then the perpendicular bisector of AB passes through the center. The center of the circle. So we want to prove this. So this statement is saying here that if I have a circle and then I have some chord AB, right? And this is any chord, I want to prove that the perpendicular bisector will pass through the center. So let's say the center is C, right? If I draw the perpendicular bisector, I want to prove that this actually passes through. So the way we prove this is we just remember another theorem, which says that if perpendicular bisector, then if on perpendicular bisector, if a point is on the perpendicular bisector, then the point is equidistant from endpoints. Or we should put it if and only if, and we say a point is on perpendicular bisector if and only if the point is equidistant from the endpoints. So the center, right, from C to A is the same distance from C to B. So by this theorem, right, the center must be on the perpendicular bisector of AB, and then that proves this theorem here. With this theorem proven, we're in a position to find our center. Because now what we can do is we can construct any chord. And we draw the perpendicular bisector for that chord. So I'm not going to go through the construction of a perpendicular bisector, but for sure there's some midpoint and there's one perpendicular bisector. Let's say it looks like that, of that chord. And you draw another chord in your circle that's not parallel to the original one. It can't be parallel. So we know, right, we're looking for the center. We know that that blue line, the perpendicular bisector of AB, right, somewhere on the blue line must exist the center. Similarly, with this pink line, if I draw the perpendicular bisector for this pink line, right, the center must also be somewhere on this perpendicular bisector of the pink chord. So that means that where these two perpendicular bisectors intersect must be the center. And this point right here is the center of my circle. So let's just recap everything that we've done and let's convince ourselves again. So First, I want to prove this statement, right? This is the key statement. This is what enables us to actually even find the center of a circle. So what enables us to find the center is that if I have some chord, right? Or better yet, this is some circle with center C, let's say, and then I draw a chord. The whole thing is that we're guaranteed that C is going to be on the perpendicular bisector because the distance from C to B is the same as the distance from A to C. So by this theorem, we have that C lies on the perpendicular bisector of AB, and that proves this idea. And then basically what we do is if we're given a circle and we don't know the center, we know that if I draw any chord inside the circle, right, that the perpendicular bisector of that chord will have the center somewhere there, and then you just draw another chord and you draw the perpendicular bisector of that chord, and where these two perpendicular bisectors intersect is the center of the circle. You just need to know how to construct a perpendicular bisector of a chord, right? You need to know how to construct a perpendicular bisector, which we've done.